Hello, this is Jack Jackson. In this video, we're going to continue our exploration of finding out which criteria will guarantee congruence of triangles. And remember, we're looking at 4 different geometries: Euclidean geometry, hyperbolic geometry, spherical geometry, and taxicab geometry. In the last several videos, we found that the side angle side condition was enough to do guarantee congruence of triangles in Euclidean, hyperbolic, and spherical geometry, but not in taxicab geometry. So let's go back to continue our work in Euclidean geometry and look at the next one. So even this is a good exploration even for, say, a high school class, or looking at the angle side angle condition in geometry, that is Euclidean geometry. So once again, we start with a point and we do angle side angle. So first, I'm going to actually do the side first. That's the one in the middle. So we do a circle here, pick a point on that circle, and connect it up and make a line segment there, and it's any point on there. It's going to have the same distance. Okay, whatever we have it set. We can make it larger or smaller here. Or we can set it by this here. Let's just set it to be 5, for example. Okay, then we can measure the angle here, which we can change by this slider. And I think that's the first one. Yeah, that one's controlled by this slider here. Okay, and so for example, that's 95 degrees, or about 1.66 radians, or 0.53 times pi radians. See a few more decimal places there. So there's an angle. Now where's the second angle? So there it's angle, side, and now the other angle has to be at B. So we put that other angle. Of course, it needs to be coming up this way if it's going to hit this ray. You can't have this one going up this way and the other one going down this way. They won't meet. And so if you see, they only meet in exactly one place. So you really don't have any choice, or there's one choice, I guess. For C, it's right there. And of course, that finishes out the triangle. And we didn't have really any choices here. And no matter how you rotate this, those angles are going to stay the same measure. Those line segments are going to stay the same measure. And so we have that we see that we get the same thing. So all of those triangles with these particular measurements are going to have to be congruent. So the next question is, can we break this? Can you make it to where there's no such triangle? Does it matter, for example, how long we make this side? Does it matter how big we make this angle? If you think about it, I think you can realize there is a way to make it not work. What do we know about triangles in Euclidean geometry? We know that these 3 angles here, these 3 angle measurements, these interior angles, must sum up to pi radians, or 180 degrees. They have to sum up to the same number every time, all right? So if you're starting with 2 and they already add up to more than pi radians, that is more than 180 degrees, or even if they add up exactly, like if these 2 add up to exactly pi radians, or 180 degrees, then these 2 lines here are parallel, 2 rays here are parallel, and they'll never meet. And if they add up to more than that, then you can clearly see that they're diverging away from each other. They're not going to meet. So you can get some measurements that you make up for angle side angle, and they're just an impossible to make a triangle of that size. And if that's the case, then we would say, of course, there are 0 congruence classes for that particular measurements, because no such triangle exists. On the other hand, if you make sure that these add up to less than pi for these 2 angles, in other words, they add up to less than 180 degrees, then regardless of what you put for the side, there will be one congruence class there, exactly one congruence class. You can make a triangle, and all of them will be congruent to each other. Okay, or looking at it from our second perspective, if you have 2 triangles And now we don't care what the measurements are, but we know that they have an angle, two angles, two pairs of angles that are corresponding and congruent, and the pair of included sides are corresponding and congruent, then they are congruent. So in other words, this side matches the side in the other one, the corresponding angle here and here match, and then you get the rest for free. Okay? And so side angle is enough. That case there, you already have the two triangles. You're not worrying about the impossibility condition. That's part of the hypothesis that you actually have the two triangles, but you don't really care what the measurements are. You just need to know that they match up and are congruent. So angle side angle is enough to make the triangles congruent, at least in Euclidean geometry. Let's check out the other three geometries next.